Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're looking at the Doppler effect. Now, what is the Doppler effect? Well, basically when you hear a racing car coming towards you, you hear the sound eeeom, eeeom. Now that sound, that change in the pitch, is the Doppler effect. Namely, when the source of the sound, or the Ferrari, is coming towards you, it's pitched high. Then as it passes you, you hear the actual pitch of the engine, and then as it goes past you, it becomes a lower pitch. So there's the yee, yum. So you're hearing a change in the frequency as something comes past you. Now here I have a little 555 chip, and it's generating a frequency, and I can make the frequency go up and down by turning this log pot, this potentiometer. So I can raise the frequency or lower it with this little device. Now that's nice, but there's another way that we can raise the frequency of something. Here I have a little organ, a little electronic organ. I'm going to press down, I'm going to switch it on, and I'm going to press down on middle C. So there's middle C, and it's pressed down. And I want you to listen to this organ and hear whether it changes frequency as I do this. Now what you're supposed to hear, as the organ approaches the microphone of the camera, the pitch gets higher, then as it comes past, it gets lower, then as it approaches again, it gets higher and gets lower. And that is, we are listening to the Doppler effect. And what I'm trying to do is I'm going to try and move this at 1 meter a second, and 1, and 2, and 3, and 4, and 5, and 6, and we're going to hear the changes of the frequency, and then we're going to try and calculate what the actual change of this note of middle C is. If we're doing it 1 and 2 and 3 and 4, what is the change of frequency? Let's try that again. There we go. Now, with Doppler, this is a reasonably easy section. It's quite nice because it's got its one main formula. And here's our organ. Here is the sound wave. Here is the person hearing it. And we're going to apply this situation to this formula. So, we've got the frequency that the listener hears. FL, the frequency that the listener hears, which we're going to try and calculate. What frequency do we actually hear? We've got the velocity of sound in the air. This is the medium, how fast sound travels through air. And we're going to take it, it's somewhere around 340, 345. We're going to use 345. Velocity of sound in air, 345 meters per second. It changes slightly depending on air conditions. So this is going to be 345, 345. Now the velocity of the listener, or the camera in this case, is the camera's velocity changing? No. The camera is standing still. Or the person that's listening is standing still. So big ears there is stationary, but the organ is moving. So the velocity of the listener is going to be 0 meters per second in this case. And then we've got the velocity of the source of the noise, and we were trying to move it 1 meter in 1 second past the camera or away from the camera and towards the camera. And at some stage it was in line with the camera. But we're going to hear the initial velocity and then we're going to hear the change of velocity. So we're going to actually do 2 calculations. One when the organ is approaching the camera and one when it is leaving the camera. I'm going to hear what the change of frequency is and try and calculate it. So the velocity of the source, we've tried to move it at 1 meter per second, both towards and then away from the camera. And then the frequency of the source is middle C. Now middle C is 261 hertz, 261,63 hertz, or 262 hertz probably to round it off. So the frequency of the source is 262 hertz. Now we know that sound, this is a transverse wave, but sound produces a longitudinal wave. Now transverse wave, the particles move at right angles to the direction of movement of the sound, which is from the source to the listener. So this is the source and this is the listener. And the direction of sound is from the source to the listener, obviously. And we're finding that 262 times a second, that's very fast, quite fast. The air is being squashed and sucked. We call it a compression and a rarefaction. I'm drawing it as a transverse wave because that's the wave that most of us are familiar with. But actually what's happening is in this zone, the crest, the air is squashed, and in this zone, the air is sucked. And this pushes, when this trough reaches the eardrum, it's going to suck the eardrum out. And when this crest reaches the eardrum, it's going to push it in. And it's going to do that to the eardrum 262 times per second when we are playing middle C. Now, different notes will produce different frequencies or tones. So, we're going to find that our frequency of the source is 262. So now we've got to plug it into this equation. The only difficult part is the plus or minus. The equation leaves it up to us. Now, let us do this equation when, first of all, the organ is moving towards the camera. When the organ is moving towards the camera, the sound gets higher as it goes past. So we must always just remember the simple fact. When a source is approaching the listener, the pitch goes up or the frequency increases. So we're going to end up, if this is the frequency of the source is middle C or 262 hertz, this frequency of the listener must be higher. It must be raised. So, if we want to raise this, what do we do? This whole thing here is just like a fraction, or it is something that is going to raise the frequency of the source. Right, now that we've got all our values, let's plug them into this Doppler equation. So, the velocity of sound in air is equal to 345 plus minus the velocity of the listener is naught, so we can ignore it, plus minus naught, over the velocity of sound in air 345 plus or minus the velocity of the source. Now we're going to have the source coming towards us first of all, and it was moving at 1 meter per second, And all of this fraction or ratio is times the frequency of the source, which is middle C, or 262 hertz. So let's see. We know that when the source is coming towards us, we must get this fraction is going to be raising this or increasing the final frequency. So must we subtract or add 1 underneath as the denominator? Well, let's think about it. If we have 345 upon 345 plus 1, it's 345 upon 346. And that's going to lower the frequency. But if we subtract 1, we've got 345 upon 344, and that's going to multiply by that, is going to raise the frequency slightly. Because 345 upon 344 is slightly greater than 1, and it's going to be multiplied by middle C, and we're going to get a slightly higher frequency. Let's work that out. So, we're going to say 345 upon 344 times 262. So we got 345 divided by 344 times 262 equals, and the frequency is going to be 262,76. So it's raised it by just 1 hertz. So that's going to be equal to 262,76 hertz. And so we see that when the organ is moving towards our camera, it raises it by approximately 3/4 of a hertz. Let's do the same thing, but when the source is moving away, then we're going to have plus 1 at the bottom. We're going to make our denominator larger, and therefore this is going to be smaller than 1 times 262, and that's going to lower the frequency. So let's work it out. When the source is moving away, again, it's going to be 345 plus minus, the listener is still 0. So plus minus 0 over 345 plus 1 times 262. So let's do the math. 345 divided by 346 times 262 equals 261,24, 261,24 hertz, and we see that that has lowered it slightly below middle C. So when our source is moving towards the listener, we're going to subtract it at the bottom, and that's going to raise the frequency. And when the source is moving away, we're going to add this to the bottom, and that is going to lower the frequency. And so we can see that the difference between 262,76 and 261,2 is approximately just less than 2 hertz. So we, with a human ear, are able to hear even a 2 hertz change of frequency as it's approaching and as it goes past. So there we go. There's a simple application of our Doppler formula. And because physics can be fun, maybe we should play it out with a little bit of music. And there we go.